Okay, so this problem is the hollow spheres problem, and this problem involves three spheres, one inside of each other, that each have their own charge, Q1, Q2, and Q3. This should be plus 1 to each of these, and so they're all inside of each other, and we want to find the electric field at a point that is outside of these two spheres, but inside of this sphere. Well, in order to do this, we can actually do a couple of tricks. The first one is we just need to know the electric field formula at this point. So remember, the electric field formula is KQ over R squared. So really, plugging that in, we're going to find K over Q. Now Q, remember, is the sum of these two. So it's going to be Q0 plus Q1 over R squared, this little r squared. Doing that, we're going to get K 4.9 minus 2.1 10 to the 6 over 0.021 squared. And that should get you an answer of 5.71 e to the negative 7th newtons per coulomb. Sorry, not negative. Just e to the 7th. That should be e to the negative 6. So why is that the case? I mean, that is very strange. Of how come we just look at these two and we totally disregard this outer sphere? Isn't this outer sphere pulling on this this electric field as well? Isn't it disrupting it in some way? Well, through a very, very lengthy mathematical formula, but simplifying it, let me explain it this way. Let's pretend that this is the Earth, right? And we have you. This is you now standing on this point in Earth, and this is a ring of satellites that surrounds you. Well, technically, though, those satellites have a little bit of pull on you, don't they? Right? So that this part of the satellites is pulling for you to go that way. Well, also, though, you have all of these satellites pulling on you to go this way. What we found is that these two forces will cancel each other out. Now, and especially because you're in this large circle, they'll all cancel each other out. Another great way to think about this is think of the moon and tides. Now, our tides change on the oceans because the moon is on one side, and so then all the water shifts to that one side of the globe. Now, what if we had a ring of moons, or better yet, a sphere of moons that completely, the Earth was surrounded in? Let's imagine the Earth in a big capsule, a big, big, huge, hollow moon. What would happen to our tides? Well, we wouldn't have any, because there would always be equal force on one side of the planet as there would be on another. That this big hollow moon that we are in would always be pulling equally on all tides. Even tides over here, it'd be pulling equally over here. That's what's happening essentially with this Q3, and that's why we disregard it entirely, because we found it always cancels each other out. No matter, even if it's really, really close, this very, very strong force will be canceled out by this very, very large, much weaker force, though, because it's further away, but much, much larger. So that's why those two will cancel each other out. Now, the second part of this problem deals with finding the surface charge density of the outer sphere. Now, that is really just, whenever you see surface charge density, remember, they're just looking for the charge over the density of the sphere, so just the surface area. Now, this charge, some people would mistake of say, okay, well, that's Q3. Well, it's not just Q3. Remember, we've got two other charges that are both causing electric field and a charge on this bigger object, this big sphere. So it's actually the sum of all the charges enclosed. So we're going to take Q1 plus Q2 plus Q3, and we're going to put that all over the surface area of a sphere, which would be 4 pi r squared. Now plugging in, and this is going to be big R, because now we're doing the big sphere. The surface charge of our outer sphere is what it's asking for. Plugging in all of our formulas, plugging in our R, you should get an answer, at least if you're using the one supplied in the description, of 4.5 times 10 to the negative 4th This would be coulombs per meter squared, I believe. So that would be your answer for the second one of the outer charge. Because remember, the density, anytime surface charge density, resistance density, they're just asking for the unit over the area or the meter or whatever there. So in this case, it's just Q, and because there's two inners, we take the sum of all inner Q's.